Hello everyone, my name is Gan Duan and my presentation today is effects of halogen in chemical exchange and porosity evolution during feldspar-fluid reaction interface. Previous research have shown that either key feldspar can be replaced by albite or albite can be replaced by key feldspar with reactions in single sodium chloride or potassium chloride solutions. Large-scale sodic and potassic alterations are always associated with IOCG deposit, and this deep sodic and shallow potassic alteration zonation is explained as either reflecting fluid mixing when original hydrosomal fluids go upward and mix with external fluids that are enriched in potassium, or the changing PT conditions as deep sodic form at higher temperature than shallow potassic alteration. However, in reactions with sodium fluoride solution at 600 degrees centigrade and 2 kilobar, sanidine can go through a self-evolved sequential sodic and potassic alteration without any external addition of potassium at constant PT conditions. You can say that the reaction product is characterized by sanidine, albite, and key feldspar zonation texture, which means that sanidine went through a sodic alteration first and then followed by a potassic alteration. Since this finding is very unusual, we want to further explore the effect of fluorine on nanometer scale reaction interface by using some high spatial resolution techniques such as TEM and Nano-sims. Here's some background knowledge. There are three reaction mechanisms for mirror replacement reaction. The first one is ICDR, interface coupled dissolution reprecipitation mechanism. This mechanism has two features. First, the dissolution parent phase would produce a thin facial fluid film at the reaction front that permits in situ nucleation and the reprecipitation of the product phase. And second, the porosity created as a result of reaction allows transportation of solute from bulk fluid to reaction front. However, some low temperature weathering suggests that there can be a 500 nanometer thick amorphous phase between unreacted phase and secondary phase, which needs to the continuum mechanism. Compared to ICDR mechanism, this continuum model, which also based on interface coupled dissolution reprecipitation process, suggests that the amorphous phase contained the precursor nuclei that permits in situ crystallization of secondary phase. And the last one is the leaching mechanism, which is characterized by the sigmoidal chemical profile due to solid state interdiffusion compared to a very sharp chemical profile in ICDR process. You can see that difference between three reaction mechanisms are based on the interface. That's why we use a different high spatial resolution techniques to study the reaction interface. First, I will give you a brief introduction of the reaction products of the experiments. We use the sanidine, which is a solid solution of sodium feldspar and potassium feldspar, to react with sodium chloride, sodium fluoride, and iron fluoride solutions. In sodium chloride solution, there are bigger porosity around 20 to 50 micron formed between reactant and product. Less than 1% grains are characterized by this zonation texture. However, most of them are just simply replaced by albite. In sodium fluoride solution, most of the grains are characterized by the sanidine, albite, and key feldspar zonation texture, and the macro-scale porosity is less developed in that in sodium chloride solution. And in iron fluoride solution, since the solution is enriched in iron, then ironite instead of albite formed a reaction front. And key feldspar, ironite, and sanidine form the zonation texture. Then we're curious, how does the zonation texture form? If we look at the reaction products formed from oxygen-16 enriched solution, you can see that both albite and sanidine are characterized by enrichment in oxygen-16, but has almost 0 amounts of oxygen-18. And the minor counts of fluorine in albite may inherit from pristine sanidine. Even though this solution is chlorine enriched, there was no detectable chlorine in albite, and small counts of silica are because of short stuttering time, which is used to avoid charging issues. And the reaction products from oxygen-18 enriched solution are characterized by enrichment of oxygen-18 in both albite and key feldspar, which means the broken down of acidic oxygen and aluminum oxygen bonds of the frame structure. And high counts between phase boundary is because of formation of fluoride. And two feldspar grains, one from the rim and one from the core, are because of different fluid alteration paths. One sample from oxygen-18 enriched sodium fluoride solution is very interesting because oxygen-18 amount is very low, which means that there was no broken down of acidic oxygen or any minimum oxygen bonds of the frame structure, which means that this sample is an unreacted sample. However, half of this grain is characterized by enrichment of fluorine, which means that fluorine can diffuse into sanidine lattice without broken down of the frame structure. We also use the focused ion beam to cut FIB foils for TEM analysis. This sample is from sodium chloride solution, and the FIB foil 1 shows the reaction interface between sanidine and albite, and the FIB foil 2 shows the reaction interface between albite and key feldspar. The reaction interface between sanidine and albite is very sharp, and the fluid path visibly propagates towards sanidine. And the sawtooth interface between albite and key feldspar is because key feldspar replaces albite along certain crystal lattice planes. All albite, key feldspar, and sanidine have identical diffraction pattern, which is a feature of ICDR process. Another sample from sodium chloride solution shows a amorphous phase near the reaction interface that is characterized by enrichment of aluminium, silicon, and oxygen by depletion in sodium and potassium. A group of irregular social lines observed across key feldspar characterized by enrichment of sodium and depletion in potassium. It may represent the fluid paths which are near after precipitation of key feldspar. In some samples, key feldspar came in direct contact with sanidine, and the phase boundary between key feldspar and sanidine is characterized by sharp and bright reaction interface, which shows stress-induced S-shaped distortion. Because of its high compressibility, it may represent a amorphous gel along the reaction front. And the identical diffraction pattern of sanidine and key feldspar suggests an ICDR process. The action products from sodium fluoride solution is characterized by sanidine, albite, and key feldspar zonation texture, as we mentioned earlier. And the reaction interface between sanidine and key feldspar is very sharp, but in the facial zone, is characterized by its complex zigzag orientation, and albite grains observed within the interfacial zone. This interfacial zone is characterized by enrichment of sodium and titanium compared to surrounding key feldspar. And similar to sodium chloride solution, albite, key feldspar, and sanidine have identical diffraction pattern, which is a feature of ICDR process, even though small grain of albite that are in direct contact with sanidine shows a small degree variations of crystal orientation. We also did a Nano-sims analysis of FIB sample from sodium fluoride solution, and you can see that albite and key feldspar have similar oxygen-18 to oxygen-18 plus oxygen-16 ratio from the right line. However, in the blue line, there is a gradient profile, which means that oxygen isotope can diffuse within this interfacial zone. So let's take a brief summary here. On one hand, the broken down arsenic oxygen and minimum oxygen bonds of the frame structure, the sharp reaction interface, and the identical diffraction pattern of albite, sanidine, and key feldspar are features of ICDR process. On the other hand, the near the path within key feldspar, the amorphous gel between key feldspar and sanidine, and oxygen diffusing along the reaction interfacial zone combines a feature of a continuum mechanism and leaching mechanism, which means that no single mechanism is responsible for our experiments. Because albite and fluoride conform as inclusions within the interfacial zone, the interfacial zone is characterized by enrichment of sodium and titanium, and as we mentioned earlier, fluorine can diffuse into the green lattice. We suggest that fluorine can play a role in the following ways. First, the dissolution of albite starts at the reaction front, and beyond the reaction front, the reactive region is progressively recrystallized. Due to the small atomic radius of sodium and titanium, compared to potassium, they can form stable complexes with fluoride. Then it results in removal of sodium from pristine sanidine, and the remaining one became sodium depleted key feldspar at the rim. And as the reaction front moves from rim to core, albite would reach supersaturation, and the resulting in the nucleation and precipitation of albite at the reaction front. This dynamic mechanism is also confirmed by reaction products from iron fluoride solution. As iron fluoride solution propagates from rim to core, it partitions sodium from pristine sanidine and precipitates sodium depleted key feldspar at the rim. Due to the enrichment of iron in solution, supersaturation leads to the precipitation of ironite instead of albite at the reaction front, And we suggest that the zonation texture is because of the selectively animous transportation with the existence of fluoride. Thank you for listening. If you have any questions, please let me know.